Hi, this is John Whitaker for the graduate level probability class, and this is our 24th video lecture, and today I want to do two examples. The first example I want to do will be an illustration of the previous fact that we had involving conditional expected values, where we introduce another random variable that might help us calculate that conditional expected value. And then the other one is more of a problem just in general about conditional probabilities and conditional expectations. Well, let us recall what we had in terms of the previous formula. So if you recall, we had the following fact, that is, I'm going to write it down here. The conditional expectation of x given y is equal to, well, it's one of two things. So here, it's the sum over w of the conditional expectation of x given w equal to w and y equal to y times L, the conditional probability mass function of w given y. And here, this is if w is discrete. And it's equal to the integral from minus infinity to infinity of the conditional expected value of x given w equal to little w and y equal to y. And here we have the conditional probability density function and probability mass function. Here's w given y and dw, dw, is the wrong thing. Dw, if, where w is continuous. Okay, so it's an illustration of that fact. Let's look at the following example. Wording example, it'll take a few minutes for us to get it up. So here's what it says. An automobile insurance company classifies each of its policyholders as being one of these types. So these types. So we've got type 1, so type 2, all the way up to type K. So the insurance company supposes that the number of accidents that type I policyholder has in successive years are independent Poisson random variables with mean lambda I, again here I runs from 1 to, depending on the type, okay. The probability that a newly insured policyholder is type I is P sub I, where, of course, the sum, as I runs from 1 to k, of P sub I, that has to be equal to 1. There's more. Given that a policyholder had N accidents in her first year, what is the expected number of accidents that she has in her second year? So that's where we're going to use one of those formulas for the conditional expectation that I wrote on the board earlier. It's going to be the one for discrete math variables. That's what we're talking about here. And then the second part of this problem is what is the conditional probability that she has M accidents in her second year. Given that she's got N accidents in her first. Okay, so let's start doing that. So two problems, really, two parts to this problem. Now, as I go to do the problem, let me write down the first part and some setup. Okay, so here's the solution. We let N sub I denote the number of accidents the policyholder has in year I. And again, I here runs from 1 to 2. So we're only talking about the 2 years, first and second year. So what we're looking at, and I'll say it this way, to obtain the conditional expected value of N sub 2 equaling of N sub 2, whatever that is, given N sub 1 is equal to N. Okay? Condition on her risk type. T. Okay? So that was the type of policyholders you could be. Now, here's what I want to point out to you. look, N1 and N2 are independent. That's what the problem says. And so really the expected value of N sub 1 given the expected value of N sub 2 given N sub 1 is equal to N. Now we'd say that these are independent, their expected value is 2. But one of the things that happens here is that we can introduce this other variable, t, which is non-independent of N2 and of N1. And by introducing this, it gives us more information to work with because we know the probability of being a certain type, P sub I. And it might help us get some kind of formulation for what this will be. And so, namely, and one thing I want to point out, even though these two are independent, the fact that you know N sub 1 is equal to little n, that might affect the likelihood of what type of policyholder she is. So there is a connection between these two, and then a connection between T and N2. All right. So here, the expected value of N sub 2 given N sub 1 equal to N, because everything is discrete, okay, or because T is discrete, it's going to be equal to the sum, I'll say, over I, well, let's call it J. J equaling 1 to K of the expected value, so using our formula, it's N sub 2 given N sub 1 equals to N and T equals to J times, well, here it would be the PMF, the conditional PMF of T given N sub 1 of J, if you will, given N, okay, that's what that is. So that's by our formula. Okay. So, if you will, that's the sum as J runs from 1 to K of the conditional expected value of N sub 2 given N sub 1 equals to N and T equals to J. And with that PMF, conditional PMF, that's the probability of T being equal to J given that N sub 1 is equal to, N itself. Okay, so that's what we have. Now, what I want to remind you of is that these two are independent. And so knowing that N sub 1 is equal to N really doesn't affect this. It may, and with the T being equal to J, because of the independence, we can reduce that part, that conditional expected value, to the sum as J runs from 1 to K of the expected value of N sub 2 given T equal to J. And here, we'll rewrite this as is. So it is the probability that T is equal to J given N sub 1 equals to little n. That's not equal to times. This should be times. I don't know why we're equals. Okay. Now, if we know that the person is type J, then when we're asked what's the expected value of the number of accidents that they will have in the second year, well, the number of accidents they will have is a Poisson distributed random variable with mean lambda. So this is going to be a sum of J runs from 1 to K of lambda sub J. Okay? And now here, this would be the probability, we'll leave this alone, as T is equal to J given N sub 1 equals to N. All right. Now we need to work on this part of the involved in our sum. Okay. Now, the probability that t is equal to j, given n sub 1 equals to n. Okay, really, we'd like to flip these. And so we're going to use Bayes' theorem to do that. So this is equal to, by Bayes' theorem, it's equal to the probability of n sub 1 equaling n. We like to flip this because knowing what the type the policyholder is affects what the number of accidents that they have. So n sub 1 equal to n given t sub j, t equal to j, that's what it's times, this will be the probability that t equals to j, all over. Now, if we use this extension of Bayes' theorem, this will be the sum over j running from 1 to k. Here, it will be the probability of n sub 1 equaling n given t equals to j times the probability that t equals to j. That's what I'll write. I might have could have used a different letter here, like I, but I've written down what it was. It's okay. Okay, so what is that? That's equal to, so here, the probability of n sub 1 equaling n, given t is equal to j, so we know lambda j is the mean, so that's the parameter in the Poisson distributed random variable of n sub 1, and so the chance that n sub 1 equals to n, it'd be e to the minus lambda sub j to the n over n factorial. Times the probability that t equals to j, well that's, if you will, we had that, that's p sub j. And then here, this is the sum as j runs from 1 to k, that's okay, we could use index of I. And here again, this j changes, so what we have is, if you will, it's lambda sub j, g minus lambda sub j, lambda sub j to the n over n factorial. So the j changes though. Lambda sub 1 is involved, lambda sub 1 to the n, then the next term is e raised to the minus lambda sub 2, lambda sub 2. So this is kind of fixed at this point. And these change here. And then this is equal to p sub j. Okay. All right. So having that information, here's what we can say. Our original problem. So the conditional expected value of n sub 2 given n sub 1 is equal to n. That's equal to the sum as j runs from 1 to k of, well, it is lambda sub j, then this. So this is e to the minus lambda sub j, lambda sub j raised to the n, all over n factorial, times p sub j. So that's what that is. So that's sum, okay, so far. And then over, so this is over this sum. So the sum, and here I'm going to have j running from 1 to k, and then it was this e to the minus lambda sub j, lambda sub j to the n, okay, p sub j over n factorial. Now, this n factorial here can come out of this sum, or if you want, this right here is going to be a particular expression. And these j's are different, so, same j, but the sums are different. So you can get some sum here that really you can pull out. So it forms, if you will, two summations. One in top, one in bottom. It would have been nice if I had changed the index here and had it I. I mean, that's good. Let's have it I. Let's make that change. Make it I. I. Okay? P sub I. Okay? That's good. Make that change. We call it I if you want. here it'd be I. This would be I. P sub I. Make that change. Let's get that change. So this would be I. Make that change. And here this should be I. I'm going to mistake several places. This is I. Okay? All right, that's good. So make that change so we can have two different sums. Because that's what the attention index is involved. Let's not let that confuse us. All right. With that having been done, we can pull out the 1 over n factorial. So we get two sums here. Sum as j runs from 1 to k, lambda sub j, e to the minus lambda sub j to the n, p, j, over n factorial. And here we have that's over this sum. As I run from 1 to k, it's lambda, no, it's e to the minus lambda sub I to the n, p sub I, all over n factorial. The n factorials are constant in both sums, so we pulled out 1 over n factorial here, 1 over n factorial here. They will cancel. And so what you get is an answer that the sum as j runs from 1 to k of lambda sub j, e to the minus lambda sub j, well, let's make this lambda raised to the n plus 1. Lambda sub j to n plus 1, and then times p sub j. Over this sum, as I runs from 1 to k, of e minus lambda sub I to the n over p sub I. And that is an expression for that part of the problem's answer. And that has to do with just the p sub i's, the lambdas involved. So it's expression in terms of items that we should have, okay, information that we should have. What n is, what lambda sub j's are, and that's what we have. Okay. Now, if we look at the second part of this problem, the probability of n sub 2 equaling m, the number of accidents is year 2 is m, given that the number of accidents in year 1 is n. Okay. And this can be rewritten, okay, as the sum, very easy to verify this, as j runs from 1 to k of the probability of n sub 2 equals to m given n sub 1 equals to n and t equals to j times the probability that t equals to j given n sub 1 equals to n. And this is common. So it's very easy to show that those two things are the same. All right. Now, here, let's expand that last part, that last factor. So this probability, the sum of probabilities of n sub 2 equal to m, given n sub 1 equal to n, and t equals to j, times. Here, this is the probability that t equals to j and n sub 1 equals to n over the probability that n sub 1 equals to n. Or, that is true, but instead, let us use Bayes' theorem again. Yes, I should have recognized this. Let's use Bayes' theorem because figuring out this probability is not as easy to do as if we know the type and we're asked about the probability that n sub 1 is equal to n. So let's use Bayes' theorem here. So this would be the probability of n sub 1 equaling n given p equals to a specific j, follows our sum, times the probability t equals to j over, here I'm going to write this with sums of the i's. So I is running from 1 to k. Here this would be p sub n sub 1 equals to n, t equals to I, times the probability that t is equal to I. There. Now, this is equal to a sum. Now, that first sum was the probability that n sub 2 is equal to m and n sub 1 equal to n and t equals to j. But due to the independence between n sub 1 equaling n, between n sub 1 and n sub 2, we can rewrite this as the probability that n sub 2 equals to m given t equals to j. So this is sum over j. And then times, now the probability that n sub 1 equals n given that t equals to j. Remember that n sub 1 is a Poisson distributed random variable. So this is e to the minus lambda sub j raised to the n over n factorial. And then the probability that t is equal to j is called p sub j, that's a symbol. All over, now this sum, as I run from 1 to k, now we had p of n sub 1 equaling m. Okay? So here, this should be n, not n. And so here, this is a probability of that happening is e to the lambda sub I, lambda sub I raised to the n over n factorial, and here we write down p sub I. So it's very similar looking to what we had before. Now, this right here we can simplify. So it's a sum as j runs from 1 to k. We write down a form for this. So n sub 2 is going to be Poisson distributed. So it's e to the minus lambda sub j, lambda sub j to the m, all over m factorial, times, so given it's t sub j, that's what we have for that. So we know this problem. Times the rest of this. So e to the minus lambda sub j raised to the n, p sub j over n factorial, all over this sum. As I runs from 1 to k, e lambda sub I, e to the minus lambda sub I. Make that change, e to the minus lambda sub I. I made a mistake. Okay. And then lambda sub I raised to the n over n factorial p dot. Okay, these n's again will cancel. And what we end up getting, to make some more room here, we can combine some terms. So what we end up getting here is a sum. So as I said before, the n factorials will cancel with each other. And so we can write this down as two sums. The first one, 1 over n factorial, will come out front. It's the sum as j runs from 1 to k. It would be e to the minus lambda sub j, lambda sub j to the m. I pulled out the n factorial already. It would be e to the minus lambda sub j, so there. Lambda sub j raised to the n, and then p sub I, p sub j. Should have been p sub j. Yeah, I made a mistake. Let's go back here for a second. I had a typo over here. Make this change. This is p sub I here, but this should have been p sub j. Make that change, p sub j. Okay, so this is all over this bottom sum as I run from 1 to k. Here, this is e to the minus lambda sub I, lambda sub I raised to the m, and that was n, p sub I, and the n factorial cancels out. And so that's a formed answer, but I'll rewrite it here to binary terms. Sum as j runs from 1 to k. I shouldn't say combine my terms, but e to the minus lambda j and e to the minus lambda j. So I've got 1 over n factorial, don't forget that. This would be e to the minus 2 lambda j. Here it would be lambda j raised to the m plus n, those two guys, and then p sub j over this sum. J runs from 1 to k. E to the minus lambda sub I raised to the n over p sub I. That's sum. And that indeed is our answer. And so that's the best that we can do with this part of the problem. Okay, I'd like to look at another example, and then that will be it for today. Okay, so this is an example. It's called the list model. And here's what it says. It says, consider n elements. So we got these n elements, E1, E2, up to En. That are initially arranged in some order some ordered list. Okay, so they got them arranged. It said at each unit of time, a request is made for one of these elements. E sub I being requested independently of its past. With probability P. Okay, this part that I just wrote means that it doesn't matter when the last time that E sub I was requested in terms of affecting its likelihood of it being requested next. So in some sense, the spot that E sub I appears in the list is independent of E sub I being requested in some sense. So the same element. Okay, so this is P sub I, so it should say. Pass for probability P sub I. Okay. After being requested, this is what happens. the element is moved to the front of the list, we want to find the expected position here's the question. The expected position of the element being requested. Okay. After this process has been going on. For some time. Okay, so let's write up what it is that we're trying to find. We're trying to find the expected value of the position. Okay? Here's the solution. Expected value of the position of the element being requested. So to compute the expected position of the element being requested. That's what we're being asked. Expected position of the element being requested. It seems like we might do something about conditionally where we have no idea about what element is being requested. So it kind of makes sense that maybe the position of the element being requested might depend, at least some part, on what's being requested. So here, or we might get some information based on that. So we will condition on which element was selected. So here's what we mean. So here's what we're looking for. The expected value of the position of the element requested. What I'm thinking about is using that formula about the expected value of a random variable here is equal to the expected value of the conditional expected value of the position of the element requested given, let's say I was selected, was requested. Maybe we gave some information by looking at it that way. I know the probability that EI was selected was P selected. That's something that's related. Okay. So here, we're doing an expected value of something that would be a random variable on the given. So that was the EI was selected. So it should be the sum over the I. So I went from one end of the expected value of the position of the element requested given EI is requested times, okay, so this would be the probability that EI was requested. Selected is what I said before, but that's what that would be, okay? The expected value of the conditional expected value. So that's what we have. Okay, now here I know what this is. That's P sub I, so I can put that in. Okay, before I do though, let's look at this. So if you want to know the position of the element requested, well, we don't know what element was requested, but here I'm saying given that E1 was requested. So this is the same thing as the expected value of the position of E1, okay? Given E1 was requested, or EI, was requested. And then symbolically, this is P sub I. Okay. Now, here, it was what was independent was the position of EI and EI being requested. Okay, those are independent. So this ought to be just the expected value of position of EI. That's what this ought to be. Now, it wasn't necessarily independent. The position of element given EI was selected. Okay? So those aren't independent. But they expected to. That's why we get this. But this should just be the expected value of the position of EI. But let's verify that. So here's how I'm going to verify that. Now, the expected value of the position of E sub I given E sub I was requested. So this is going to be a sum over the positions of EI, which I'm going to label as K, running from 1 to N, okay, of the position of EI and the same thing as K, times, okay, so here I'm doing a conditional expectation. It's the sum over all output values of this, of all output values of this, times, it was that conditional, in this case, the probability mass function of position of EI and EI was requested. So it would be F of the position of EI given that EI was requested. What that is the probability of the position of EI and EI is requested over the probability that EI is requested. But due to the way the problem is worded, these are independent events. So that's equal to the sum over the k running from 1 to n. Here this would be k, that's the position of the I, times, yeah, I'll write down the position of vi equal to k, so that's k, times the probability of the position of EI equal to K. I'll put equal to state parentheses again. Okay, so here, this is nothing more than the expected value of the position of EI. I think that's what this is. It's the expected value of K, which represents the position of EI. Okay. Now, what we have then is, so the expected value of the position of the element requested that's equal to a sum, what we had before, as I runs from 1 to n, it would be the expected value of the position of EI, okay, times PI. So now we've got to figure out this. It wouldn't make any headway with the expected value position of EI. Okay. Now here's what we're going to do to help us find. So we're going to find this indicator function. So find I sub j equal to 1 if E sub j proceeds E sub I. So I'm trying to figure out the position of the E sub I. So it's 0 otherwise. So what I'm going to do is to figure out the position of E sub I. I'm going to have this I sub j, and what's it going to be equal to? It's going to count, it's going to indicate whether E sub j it precedes E sub I. So to find out the position of E sub I, I'm going to sum up these I sub j's, and that'll give me something about the position of E sub I. Here's what it gives me. Now, the position of E sub I is going to be equal to, okay, so let's say I summed up all the I sub j's, 1, 2. 1 to n, of course you can't have j equaling to I in the case. But, and I said the answer was 5. Then that means that there were 5 elements in front of E sub I, the one we're interested in. And so that means that E sub I would be in the 6th position. So E sub I in general is 1 plus the sum over all j's different than I of I sub j. That's what we have. All right. So that's what the position of E sub I is. So then we want to know the expected value of the position of the element selected okay, that's our original problem. Okay? Well, that's equal to, we have a sum as I runs from 1 to n of the expected value of the position of E sub I times P sub I. But what we just said was this expected value of position of E sub I, well, the position of E sub I is this, so it would be the expected value of 1 plus the sum over j's being different than I, of I sub j times P sub I. So we'll work with this, maybe we'll make some progress with that. That's equal to the sum as I runs from 1 to n of, well, it would be the expected value of 1, that's just 1, times the expected value over the sum as I or j is different than I of I sub j times P sub I, which is equal to, okay, so this is the sum as I runs from 1 to n, and this would be, if you will, 1 plus the sum as j is different than I of the expected value of the I sub j, and then all that times P sub I. I can distribute this P sub I. This is equal to the sum as I run from 1 to n of P sub I, and then here this will be plus the sum as I run from 1 to n of this part. So it's the sum over the j being different than I of E sub I, E sub I j, expected value of I sub j. And then this is time P sub I. Okay. Well, the sum of all the P sub i's, well, that's the sum of all the probability mass function values, and that's equal to 1. Plus, here, this is the indicator function here of P sub I. That's the probability that event happens. And so this is equal to the sum over all the I values. And here, this would be, if you will, I'll pull the P sub I out, sum j being different than I, of E sub I j. Okay. So this is equal to 1 plus sum as I run from 1, this should be n, of P sub I. And what is this? This is the probability. This is the sum over j's being different than I. This is the probability that E sub j proceeds, comes before E sub I. Okay, that's what this is. Okay, so now maybe we can make some headway on what that is. We can. This is a very, well, involved, difficult problem. So if we can follow along, that would be great. Not thinking we could have created this on our own, maybe. Maybe that's too big. But here, maybe we could follow it along. That's good. Understand the solution. All right, so here's what we have. We're almost through. Now, the probability that E sub j precedes E sub I can be computed. By noting E sub j precedes E sub I if and only if the most recent selection recent request. I'll put it that way. For either E sub j or E sub I is for E sub j, was for E sub j. Because remember how the list works. Whatever was requested most recently goes from. Okay. So, the probability that E sub j proceeds is what we're interested in. E sub I it can be rewritten as the probability that E sub j was selected given, okay, I need a little bit of room, so the given part's right down here. Either E sub I or E sub j was selected. So one of them, when one of them was selected, it was out. That's what happened. Okay, so let's use our definition of conditional probability here. That's equal to the probability that E sub j was selected and E sub I or E sub j was selected over the probability that E sub I or E sub j was selected. Okay. These in the bottom are mutually exclusive events. And in the top, this is the same thing as probability that E sub j was selected. So this is probability of E sub I plus the probability of E sub j. But I have symbols for those. That's P sub I over P sub I plus P sub j. So, this concludes it. The expected value of the position was equal to 1 plus the sum as I runs from 1 to n of P sub I times the sum as the j being different than I of P sub E sub j precedes E sub I. Okay. And so we have at least a way to write this just in terms of the p's. P sub i's or P sub j's. So this is equal to 1 plus the sum as I run from 1 to n of P sub I times the sum as j is different than I. It was P sub j, I think. That's what it should be. You know what? I wrote down the wrong one. Let's back up. That's wrong. Right here. So here, the E sub j being selected, it has a probability of P sub j. So that's what this should be. P sub j. You know, for instance, make that change. Okay, so here writing our final answer. P sub j over P sub I plus P sub j. And that's the best that we can do. That concludes the solution of this example, and it concludes this lecture. Thank you very much.